Uh-huh.
right? Sometimes it's like it's either horrifying or amusing depending on how you
Hmm.
look at it, as the Grok Mecha Hitler incident, right?
Yeah.
Where they basically they well, I mean, first I guess Elon Musk specifically wanted to build Grok as an anti-woke chatbot, but then
Yeah.
because it's trained on the same data as all the other chatbots, it is still pretty woke, right? It's still, or it's,
Yeah.
or it's, or you could say, so some people would say, like, yeah, it's saying, that the 2020 election was not stolen, the COVID vaccine is effective, just because those are true statements,
Uh-huh.
right? Those are, indeed supported by the evidence, but this was not what, this customer base wanted to hear.
One. Okay, I'm here with Scott Aaronson. Scott, thank you so much for coming. It's great to have you.
Yeah, it's great to be here. Thanks.
Yeah, it's great to talk with someone who is extremely deep into quantum mechanics and more specifically quantum computing, because I think most people don't understand this at all, and even they won't dare to say they understand because the rigor of the physics they think it's required. So, and I think it was Richard Feynman who said something like nobody understands quantum physics or something like that. So, where do you think people get this one from, or maybe they approach it from the wrong direction?
I think that there are sort of two different things coming together, right? One is that, quantum mechanics is 100 years after its discovery, right, remains genuinely, one of the most mysterious things that humans have ever discovered about how the world works, in the sense that, like, experts still don't agree with each other about, what is it saying about reality, right? Even though they all know how to use it, they all agree on how to use it to calculate the probabilities of experimental results, right?
Mm, yeah.
So, so that's one thing, right? That it is, profoundly mysterious, and what it means about the
Mm,
underlying reality that tells us that we need to use these rules. But then the second thing is that people got the impression that, if you want to actually learn this or understand this, then you have to learn just an enormous amount of physics and math first, right? You have to learn, classical physics, electromagnetism, and then understand, like, the whole history, of that sort of led physicists to,
mhm,
abandon the classical picture of the world, the black body paradox, the crisis of the stability of atoms, and on and on. And that, to understand quantum mechanics, you would have to deal with differential equations, with integrals, with infinite dimensional spaces, with, it just sounds really terrifying. And I think that second aspect, from a modern perspective, is greatly exaggerated, right?
mm,
From the point of view of quantum computing and information, my field, right? How we think about it now. No, to really engage with quantum mechanics, what you need to know about are complex numbers and vectors and
mm.
matrices and probabilities. Okay,
Okay.
so there's so I would say, the amount of math that you need is not zero, but it's an amount that many people have, let's say, who are undergrads in college, who are not physics majors, or even in many cases in high school, right? And
Mm,
so it sort of, it expands by at least an order of magnitude,
right.
the number of people who have the prerequisites to learn this stuff. And um and and uh, it, it it's not that the physics is not important anymore. It's just that you can change the order in which you learn things, right? Like, once
Mm,
you understand the basic logic of quantum information, which only requires, vectors and matrices and probabilities and so forth, then I think, you're in a much, much better position to go and learn something about the physics, right?
Mm,
And
okay.
that's been my experience. That's been the experience of many people who got into quantum computing and information, originally from math and computer science, rather than from physics.
Mm, okay. Great. How do we build a scalable quantum computer?
Well, there are groups all over the world who are spending billions of dollars right now to try to figure out the answer to that, right? I mean, we won't know for sure how what's the best way to do it, whether it's even possible to do it until someone has done it, of course. Okay, but having said that, the basic ideas of how you would build a scalable quantum computer have been in place for 30 years now. Okay, they've been in place since
Mm,
the mid 1990s. So, um, the basic idea is that we want to build a computer whose basic elements are quantum bits or qubits. Right?
uh,
These are bits that can be maintained in a superposition of a zero state and a one state. Um, a huge variety of different physical systems could serve as qubits. So you could use atomic nuclei, okay, and where like if it's spinning clockwise about some axis, that's a zero, and if it's spinning counterclockwise, that's a one. Right? That's what people do in what's called trapped ion quantum computing. Okay, you
mhm,
could use photons as your qubits, the polarization or some other state of a photon. That's what people are trying to do in optical quantum computing. Okay,
mm,
and there are also companies doing that now. Okay, you could try to use the state of current around a superconducting wire. Okay, which
mm,
is which could be enormous by qubit standards, right? Like nearly big enough to see with the naked eye, right? But
mm,
but behaves quantum mechanically because it has been cooled to nearly absolute zero. Okay, this is what the superconducting quantum computing groups, including Google and IBM, are trying to do. Okay, so you have all these different approaches, being pursued in parallel, all of them with sort of the same underlying logic, right? You want a programmable system where I have a whole bunch of qubits. I can initialize those qubits. Let's say like
mm,
put them into the zero state. I can do operations on them. Okay, which would include one and two qubit operations. Okay, the qubits have to be able to interact with each other to
right.
form entangled states. And they have to do that in exactly the way that I specify, right? I want them to do I want a single system that will do any computation of my choice, and then I need
Mm,
to be able to measure the qubits, okay, to get a probabilistic sample, according to the predictions of quantum mechanics from the state that they were in. Okay,
mm,
now the central difficulty in doing all of this was recognized from very early on. And it's that, in order for a system to behave as a qubit, it has to be incredibly well isolated from its environment. Okay. And this is a requirement that we don't have in classical computing, right?
mm,
With,
yeah.
with, with classical computers, also they are subject to error. I mean, with integrated circuits, of transistors, right? The rate of error is ridiculously small, right?
Mm,
But on your laptop, there will be a few errors per year when a cosmic ray, for example, passes through the
yeah.
chip. Okay, and if you're operating a data center on the scale of Google or Amazon, let's say, then you're certainly worried about cosmic ray errors and how to error correct them, right? So, a quantum computer, would also suffer errors that would need to be corrected. Okay, but there the problem is much more severe in a certain sense. Okay, and
Mm,
the
okay.
reason for that is that if the rules of quantum mechanics tell us that if you have a qubit, let's say, that's in a superposition of zero and one, right? So
Hmm.
it's a linear combination of both possibilities, right? But then the information about whether it's a zero or a one leaks out into the environment in any
Mm,
way,
right.
right?
Yeah.
So it could be because someone came and measured it. Okay, but it doesn't have to be a person who measured, right? Or any
Hmm.
living organism. It could be just this qubit, became correlated, entangled, with some other particle that just flew away, and it flew away in a different path, depending on whether that qubit was zero or one, right?
Mm,
Then,
okay.
if that happens, then the effect on the qubit will be exactly as if someone had measured it. Okay, which means and measurement in quantum
Mm,
mechanics is a destructive operation. Okay, it's like
hmm.
you ask a qubit if it's zero or one. Now you force it to decide. You force it to make up its mind, and it gives you one of the answers probabilistically. Right, and the heart of quantum mechanics, by the way, is just a set of rules for calculating what those probabilities are. Okay, so we know how to calculate them, but once you make a measurement, then it snaps to one or the other. Okay, and whichever one
Mm.
it picks, it sticks with that. So if the qubit tells you it's zero, then it now is zero, right? And
Yeah.
look again, it's still going to be zero. So you've lost the superposition. Okay, and so we want this to happen, but only at the very end when we're ready to measure the result, right? If it happens prematurely, then it's as if the environment is constantly looking at our computation, looking at our souffle while it's in the oven, while it's baking, right? And that sort
Hmm.
of constantly forces it back to being in a classical state. And now we lose the advantages of being in a quantum superposition. Okay, so
Mm,
so
yeah.
what this all means is that if you want to build a scalable quantum computer, then you need some way of keeping the qubits incredibly well isolated from their environment. Okay, um, but they can't be perfectly isolated because something has to come in and tell them what to do, right?
Mm,
Something has
right.
to, cause the qubits to interact with each other, in this precisely choreographed way. So, this is such a hard problem that there were distinguished physicists in the 90s who said, you will never do this. You will
Right.
never, it's just fundamentally impossible. Maybe you'll build one with 3 or 4 qubits, but you will never build a quantum computer with millions of qubits because errors will just obviously creep in and destroy everything by the end. Now, there was a huge discovery in the mid to late 1990s that sort of changed the opinions of most of us about this. Okay, and that was called the theory of quantum error correction, right?
Mm,
And so this was not obvious to people, okay? But it turns out that once you get the rate of physical errors in your qubits to be low enough, then there are these very, very clever quantum error correcting codes that can take you the rest of the way. Okay, so basically what you do is you encode your logical qubit. That is the thing that you really care about, its superposition of zero and one. You encode it across the state of a large number of physical qubits, like
mm,
maybe
right.
dozens or even hundreds or thousands of physical qubits. Okay, in some entangled, so there will be some entangled state of all these physical qubits that represents a zero, some different entangled state of
Mm,
all those different physical qubits that represents a one, and then superpositions of the two will represent a superposition of zero and one. And these codes are designed with the property that even if a small fraction of qubits get destroyed or leak their state into the environment, you can detect that by a
mm,
measurement on the remaining qubits, and you can correct it. You can fix it, and you can recover your original quantum state. Okay, and crucially, you do that via measurements that don't tell you what is the state of your logical qubit. Right, that you
mm,
don't want to know, right? If you learn that, that
yeah.
would destroy the logical qubit, right? So you only make measurements that tell you, has an error happened, and if so, what do I need to do to fix it? Okay, and a further key fact is that if there were like a bunch of little tiny errors, like little continuous rotations that you don't want, right? You can view those as just a quantum superposition of certain, discrete, certain combinations of discrete errors, either
Mm,
happening or not happening, right? So sort of quantum mechanics has this effect that it discretizes the errors, right?
right.
Each error either happens or doesn't happen. Once you make a measurement, you force nature to decide, has the error happened or not? And then if at most a small number of errors have happened, then these codes can correct them. So now we have a new vision of what a building a quantum computer would entail. Okay, that
Mm,
if I want a quantum computation with a few thousand logical qubits, then I may need millions of physical qubits. Okay, these qubits are being continuously, measured and refreshed, to see, detect if errors have happened, correct the errors if they have happened, right? So now, my quantum computer is no longer an isolated system. It's not
hmm
closed. It's not, in the technical term would be unitary. Okay,
Yeah.
it's not fully
hmm
closed to the environment. We are using good interaction with the environment in order to counteract the bad interaction with the environment. Okay, and we are sort of continuously stabilizing our quantum system, and then
mm
we're doing operations on these logical, encoded qubits that eventually, have the effect of doing our quantum computation. Okay, and there are estimates now that if you wanted to build a quantum computer that would, let's say, factor a 2,000 digit number, which is
mm
one of more impressive, one of the more dramatic things that we know that a quantum computer would be able to do, right? Then
Yeah.
you might have to fill a building with, dilution refrigerators,
Yeah.
or with ion traps that would be shuttling these millions of physical qubits around. Okay, and it might take a week. Okay, it might take a
Mm.
week. Once you factored in the need for all of this error correction, but it looks like this is now, quote unquote, merely a gigantic technological problem, right?
Yeah.
There's no new principles of physics that ought to be required here to make this work, and then the result of that computation would be something that, with the best classical algorithms that anyone knows, at least in public,
Uh-huh.
running on the largest supercomputers that we have, could take longer than the age of the universe. Okay,
Mm.
for
Okay.
this, I hesitate, or sorry, I hasten to add, for this specific problem of factoring numbers. For many other problems, you would not get such a speed up. Okay,
Mm.
but this is the sort of the current vision of, what the companies like Google, IBM, Amazon, and all these venture-backed startups, like every cute name involving the letter Q,
hmm
Quantinuum, PsiQuantum, IonQ. This is what all these companies are aiming for in different ways.
Okay. Okay, right. But some physicists believe that there will be like physical obstacles rather than just technological ones
Yeah.
that will prevent quantum computers from being built. How do you address this?
Yeah, so there remain skeptics who, there remain people who don't even believe quantum mechanics itself,
Yeah.
right? They think, it's an approximation, it's worked, every time for the last 100 years, but that doesn't mean it will continue to work. And it just what it says about reality is too crazy, so it has to break down at some point once systems get sufficiently large or complicated, right? And then there are other people who say, no, we believe quantum mechanics. We have no problem with quantum mechanics, but there must
Mm,
be some new principle on top of quantum mechanics that would censor quantum computing. Right, that would
okay. Yeah.
render quantum computing impossible. So, for example, maybe there are some highly correlated errors that would violate the assumptions that are made by the theory of quantum error correction, right? And
Mm,
that would go outside of the errors that the types of errors that these error correcting codes can handle. And what I
right.
say to both of those groups of people is, man, I hope you're right, because if you're right, then
Okay.
that's a revolution in physics, right? Then what an opportunity to learn some dramatic new thing about the world, right? For the quantum computing people to be right is the more boring possibility. It's the more
Mm,
conservative possibility, right? It's just if everything about physics works like we think it does, then a scalable quantum computer, however difficult from an engineering standpoint, ultimately ought to be possible, right? Like if it's not possible,
mm,
then there is something deep that we don't understand about the physics. Uh, and so I say, either way, let's find out, right?
mm.
Let's learn something new by trying this and seeing what happens, right? I mean, a breakdown of quantum mechanics itself would be, the biggest revolution in physics for literally for 100 years.
Yeah.
Okay, so and actually for me personally, this is like the number one application of a quantum computer. More important than simulating quantum physics and chemistry. More important than breaking cryptographic
Mm,
codes. It's just proving the skeptics wrong,
mm.
right? It's just,
Okay.
or as we could say it, it's just testing quantum mechanics itself in the maybe the most severe way that we're ever going to test it. Okay,
Oh,
so
okay.
so I think absolutely. Let's do this. Let's see if the skeptics are right. Some of them have actually I'm thinking of a mathematician named Gil Kalai, right?
Uh,
They've actually proposed like specific models of what they think would break. Those models have not fared well. Okay,
mm,
given the experimental progress of the last decade. I think some of them have already been refuted by experiment, right? Like if Gil Kalai was right, then the we should have already he's an example of someone who believed in these sort of what I call conspiratorially correlated errors. Right. And then, if those were there, we should have already seen them in the experiments that
mm,
Google, for example, and Quantinuum and others have done over the last 6 or 7 years, but we haven't seen them, right? Instead, we've seen that the errors look for all the world like they are just independent, on each qubit,
okay.
which is the kind of error that these error correcting codes can ultimately handle. Um,
Mm,
so far everything is looking like yeah, it's like the theory of quantum error correction assumed in the 90s. This should merely be a staggering engineering problem, no new physics required, right? All the experimental results of recent years have been consistent with that. Just in the last year, we saw the first experimental demonstration of an error corrected qubit, a
mm,
logical qubit that actually gets better as you use more and more physical qubits. Okay, that was
mm,
what
okay.
Google did this past December with their 103 qubit superconducting chip. Okay, so far, it looks like yes, it is staggeringly hard from an experimental standpoint. No one ever said it wouldn't be, but there's been massive progress over the last 30 years, the last 20 years, the last 10 years. We are much further than we were certainly when I joined this field in
Yeah.
in what can be demonstrated, and there is no sign, zero sign of any exotic physics that would make this impossible. Right now, of course, it could be that it will just be too hard. Right, like we won't discover any deep reason why it's impossible, but the funding will run out, or
Mm,
people will lose interest, or
right. Yeah. Yeah. Yeah.
civilization will collapse.
Yeah.
Something I worry about these days, right?
Yeah.
Before we are able to do this, right? People often use the example of nuclear fusion, right? Which we know is possible, right? I
Mm,
mean, the sun does it, hydrogen bombs do it, right? But controlled nuclear fusion, right? It's been only 10 years away for like
mm,
60 or 70 years, right? It
yeah.
just it seems to keep receding past the horizon. But I think also with nuclear fusion, eventually, I am reasonably optimistic that if our civilization continues, then eventually we will get controlled nuclear fusion and we will
Mm,
get scalable
okay.
quantum computers because the laws of physics are in favor.
Mm. So I think you said there in the
Yeah.
middle, but what do you think will be the most important application of quantum computing in the future?
Yeah. So okay. Well, so I like to joke that for me the number one thing is just making Gil Kalai admit that he was wrong, right?
Yeah.
And it really was possible to build a scalable quantum computer that outperforms a classical one. But economically, I think that the most important application remains the one that Richard Feynman
Mm,
and other physicists were talking about 45 years ago when they
hmm.
first proposed the idea of a quantum computer, and that's just simulating quantum mechanics itself.
Okay.
Right.
Yeah.
So it's anytime you are trying to design a new material, like a high temperature superconductor or a new battery, potentially a new solar cell, or a new chemical reaction, different way of making fertilizer, right? You basically have a many body quantum mechanics problem, right? You have
Mm,
some complicated molecules with lots of electrons in different orbitals that are forming some crazy entangled state, right? And now calculating what's going to happen, involves keeping track of that state, right? And
mm.
chemists and physicists have known this for generations. They've known it mostly as a practical problem. Like if you're
Yeah.
trying to simulate quantum mechanics on a conventional computer, right? Then you very very quickly hit a limit
Yeah. Yeah. Yeah.
in what you can do. So this is why for a long time chemists and physicists have been extremely interested in inventing approximations.
Mm,
Okay, that often in practice let you cut through that complexity, that sort of exponentiality in these quantum mechanical amplitudes, right?
okay.
That quantum mechanics is all about at the core, right? And they've won Nobel prizes for some of these approximation methods, like density functional theory, for example. Okay, but sometimes those approximations don't work, right? And so the original idea for a quantum computer would be, well, if nature is giving you this lemon, why don't you make lemonade out of it,
Mm,
right?
yeah.
Why don't you build a computer that itself would have this same exponentiality? This would itself be built out of qubits that would be able to go into these entangled superposition states, and then possibly get an exponential advantage for the problem of simulating quantum mechanics itself, right?
Okay.
Or
Okay.
or rather, we could say it would not suffer the exponential slowdown that classical computers suffer when they are
Uh,
trying to simulate quantum mechanics, right?
yeah.
Because it itself is quantum mechanical. Okay, so I think that despite all the progress in the field, my personal opinion is that remains the most important application economically. It's what a quantum computer was born to do in some sense, to
Mm,
solve
okay.
problems that are themselves quantum mechanical, right? And you have, that could potentially be useful, as I said, to the materials industry, to biochemistry, to drug design, to all sorts of industrial processes, right?
Mm, yeah.
So uh and and even then it's not obvious because people have gotten really really good at finding good enough approximations using classical computers,
Hmm.
right? And so you have to, the hard part with quantum computing is that it's never enough to just do something with a quantum computer. For it to be economically useful or valuable or interesting, you have to beat the best that could be done using a classical computer, right? That's often the sticking point. Okay, that's
Yeah.
often
Yeah.
the
Yeah.
hard,
Yeah.
right?
Right.
But with quantum simulation, I feel like there would be hundreds of different shots on goal, right? And
Okay.
if you could outperform, the best classical approximations for even just a few things, then those could be billion-dollar industries, right?
Mm,
Uh, okay, but now this is not the application that got most of the world excited about quantum computing,
hmm.
right? Despite its importance, right? As long as it was quantum simulation, quantum computing just remained this weird idea that a few physicists were talking about, like through the '80s and the early '90s. right? Now, the big discovery that really put quantum computing on the map was that sometimes, in a few special cases, you can get a quantum computer to give an exponential speed up for even for
Hmm.
problems that have nothing to do with quantum mechanics. Okay,
Okay, okay, okay.
and the most famous example here is called Shor's algorithm, which was discovered in 1994, so 31 years ago. And Shor's algorithm is an algorithm for solving certain specific problems in number theory and group theory. Okay, so for example, finding the prime factors of
Hmm.
an enormous composite number. Okay, this algorithm can be used to factor a composite number, which is n digits long, using a number of operations that grows only like n squared, roughly.
Okay, yeah, yeah, yeah.
Um,
Right.
and now, just for comparison, the best classical algorithm that we know for this problem, after more than half a century of people seriously thinking about it, uh, is takes time that grows exponentially with the number of digits. Okay, or strictly speaking,
Hmm.
exponentially with the cube root of the number of digits. Okay, but we would
Okay,
still
right.
call that exponential, right? And now, why do we care about this? Well, anytime you visit a website with HTTPS, right, in the URL bar, right, anytime you are sending your credit card number, say to order
Hmm.
something from Amazon, or you're sending a chat message over Signal, right, your
Yeah, yeah, yeah.
data is being encrypted by a code whose security depends on the belief that factoring
Hmm.
is hard, or that a few closely related problems in number theory are hard, which Shor's algorithm would also be able to solve. Okay,
Okay,
so
yeah.
with once Shor published his algorithm, and it became clear that if and when someone can build a really scalable, error corrected quantum computer, then they can break almost all of the encryption that protects the internet, then as now, right? So this is these are the public key cryptographic codes that are just built into how we have used the internet since the 1990s. And this would mostly be a it could be a boon to whichever intelligence agency or criminal syndicate were to get this capability, if no one
Okay.
else knew, especially if no one else knew that they had it, right?
Hmm.
It could be a huge temporary boon to them, right?
Hmm.
And over the long term, what it means is simply that we would all need to upgrade our methods of encryption to what are called quantum resistant cryptographic codes, right?
Okay.
So
Okay,
there's
awesome.
been a lot of research on that as well, and today we know pretty good candidates for just purely classical cryptographic codes that would resist Shor's algorithm, right? No one can prove that any of this is secure, right?
Hmm.
Either against the classical computer or against the quantum computer, right? These are some of like the hardest unsolved problems in all of math. To just prove that these problems require exponential time, we don't know how to do that. But in any case, none of the known methods work to break these systems with either a classical computer or a quantum computer. And so there already is a push to migrate to these quantum resistant systems. I
Hmm.
was at a conference this year where people from NIST, the U.S. agency, and the
Hmm.
National Security Agency, the NSA, were there, and basically saying that by 2031, they want every federal agency in the U.S. to have the capability of switching to quantum resistant encryption.
Okay.
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 Which by government standards is like a lightning fast schedule, right?
Yeah.
But and I think by 2035 or something to actually be using quantum resistant encryption. And I'm sure that if someone builds the actual large quantum computer running Shor's algorithm, then that will, that will accelerate the kind of timelines that people talk about. Okay, but
Hmm.
Google and other companies have already started migrating to quantum resistant encryption. All the
Mm.
cryptocurrency people are talking about this and are worried about it. Right.
Yeah.
So Bitcoin, Ethereum, they all use digital signature schemes that would be vulnerable to Shor's algorithm. Okay,
Mm.
with Ethereum, the good news is that at least like someone is in charge, right? There's
Hmm.
this, engineering team or council that can decide like we are going to migrate to quantum resistant encryption. With Bitcoin, no one's in charge, right?
Right, right,
So
right.
like, like there's no one, a Satoshi has vanished, right? And so, there's no one to make the decision,
Yeah,
uh,
yeah.
uh, to do this. And apparently, the more recent Bitcoin wallets are protected by additional layers of encryption. But whoever first built a quantum computer with Shor's algorithm, they could potentially steal tens of billions of dollars in early Bitcoin wallets, including
Mm.
Satoshi's own Bitcoins.
Okay.
Um,
Okay.
yeah, which is a very strange thing. Okay, but I hesitate to put this forward as a positive application for humanity. Uh,
Mm. Hmm.
so then you could say that like for 30 years, the goal in quantum algorithms research has been to try to broaden the list of applications of a quantum computer beyond these two areas, beyond number one, quantum simulation, and number two, breaking these public key cryptographic codes using
Okay,
Shor's
okay.
algorithm, right?
Huh.
And we do have more examples, okay? But the additional examples that we have usually either the quantum advantage is more modest, or it's more speculative, or it's for some very specialized problem.
Okay.
It's usually at
Yeah.
least one of those three, right? And so I think this is very important for people to understand because there's a tremendous amount of hype, right? Certainly, although not only from the companies that are trying to, raise all this money from investors, right? But saying basically quantum computers are just the next computer. They're just going to revolutionize everything. Okay, AI, machine learning, optimization, finance, no matter what it is, quantum computers will just be exponentially faster at it. Okay,
Hmm.
that's that's like more than 90% BS, I would say.
Okay.
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 Uh like for in all of these areas, we do know some quantum algorithms that could give some speed ups, but but the scope of those speed ups is a very hard question. So beyond Shor's algorithm, there's another quantum algorithm called Grover's algorithm. I mean, this is maybe like the second most important one, discovered in 1996. Okay,
Hmm.
and what Grover's algorithm does is it can take any problem where you have n different solutions that you're trying to search through, right? And where let's say you know how to recognize a good solution if you see it, but you're looking for a needle in a haystack, basically, right? And
Okay.
it lets you search through that haystack of n possibilities in with a number of steps that grows only like the square root of n. Okay, so
Mm.
it's a square root speed up. Okay,
Mm.
and
Okay.
now compared to Shor's algorithm, Grover's has an enormously wider range of applications. Right, like
Mm.
like like if you look at a computer science textbook, half of what's in it will be problems that have some component that could be Groverized. That just look like okay, I'm going to try each of these n things, or I'm going to search through this database looking for a record that I want, right?
Okay.
So
Okay.
that's an enormous number of applications, and and
Hey.
even beyond the obvious ones, we've managed to generalize Grover's algorithm by quite a bit over the ensuing decades. Okay, the drawback is that it's not an exponential advantage, right? It is merely a square root advantage.
Okay.
So like, the square root of a million is 1,000. That's pretty good. But if someone had needed to search through 2 to the 1,000 power possibilities, well, the square root of 2 to the 1,000 is 2 to the 500. Right? Still a very big number. right?
Okay, okay.
So, so yeah, and often people will say, well, okay, but it sounds pretty good, right? That's certainly not nothing. I would take that square root. Okay, the trouble is to build a fault tolerant quantum computer,
Mm,
in any way like we understand today, is going to incur an enormous overhead, right? Which
hmm
could easily be by a factor of a million or more. Right. So now,
mm,
like, if n is the number of solutions that you're searching through, right, the question you need to answer is how big does n have to be before a million times square root of n is less than n?
right, right.
Right. That's when Grover will start winning. Okay, over
Mm,
over a classical solution. And the answer is that, well, that starts winning when n is in the trillions. Okay. So, like, eventually you should be able to get an advantage from all these Grover based approaches, but it might be, quite far in the future, even further than let's say using Shor's algorithm to break cryptographic codes. So that's Grover. And then, for several decades, people have been looking for quantum algorithms that would have broader applications, like to machine learning and to optimization, and that would do better than Grover, that would
okay.
get better than that quadratic advantage. And they have some candidates, and some of them are really interesting. Like, man, it'll be great once we have the large quantum computer and we can try these algorithms out. And we can see
hmm
empirically, like, is there some class of inputs where they really give us a win? The trouble is, we need a win not just compared to classical brute force, but we need
Right.
a win compared to the best classical heuristic methods that anyone has come up with, like
Mm,
simulated annealing, and now we have to compete against, the best classical solutions that AI can find, right? That neural nets can find, right? And that may set the bar even higher. Okay, so I think that there will be applications of quantum computers in all of these areas, eventually. But the huge initial applications are going to be, number one, breaking public key cryptography. Number two, simulating quantum physics and chemistry themselves. And then, and we continue to look for more applications. We continue
right.
to look for, there may be other things that no one has even thought of yet. Of course,
Yeah,
that's possible
certainly.
as well.
Okay.
Yeah.
So the next topic that I want to talk with you is AI slash AGI. So do you agree with David Deutsch's take on AI that basically AGI is going on the opposite direction of AI because um like if you AI like is always kind of confined to meet a solution. So even if you present ChatGPT a problem and he can't possibly solve it, he will give you a wrong solution. And another
Mm.
thing is that AIs are obedient, so
Mhm.
they will
Yeah.
do exactly what you tell them to do. Um, so and AGI would require creativity and a capacity for
Yeah, so
generating
so I'm so I'm not
explanations.
I'm not- I'm so I'm not sure that I see the sort of sharp dividing line that that
Okay.
that David Deutsch apparently sees there. I mean,
Mm,
certainly, we see, every day now, language models doing things that, the companies that created them did not anticipate or intend.
uh-huh.
Right. I mean, sometimes it's like it's either horrifying or amusing, depending on how you
hmm
look at it, as with, the Grok Mecha Hitler incident, right?
Yeah, yeah.
Where they basically, well, I mean, first they, I guess Elon Musk, specifically wanted to build Grok as an anti-woke chatbot. But then,
Yeah.
because it's trained on the same data as all the other chatbots, it is still pretty woke, right? It's still, or it's,
Yeah.
or it's, or you could say, so some people would say, like, yeah, it's saying, the 2020 election was not stolen, the COVID vaccine is effective, just because those are true statements,
Uh-huh.
right? Those are, indeed supported by the evidence, but this was not what, this customer base wanted to hear. And so they sort of did something, to sort of tell it to be less and less woke, and then it went too far, right? It said, okay, it started praising Hitler, right? It was
Yeah,
almost
yeah,
like a parody of what they ask for, right? Which, I don't think that even XAI, wanted to create a mecha Hitler, right?
Hmm.
So certainly, you could call that disobedience, right? Or if you say, if that's not disobedience, then
Hmm.
it's an interesting question. Like, what would it have to do in order for you to call it disobedient, right?
Yeah.
Like even the most disobedient human, right? You could say, well, they were after all, they were obedient. They were obedient to what their genes or what their brain
Hmm.
chemicals, were
Right,
telling
right.
them to do. Right? It's that the word obedient sort of takes a second input. Right? Obedient to whom? Right? To what? I tend to be very skeptical of of anyone who says, okay, all the LLMs that we see, they're all, clearly, limited in some way that humans are not, right?
Okay.
Because the challenge for that person is always, okay, then show me your test, right? Give me the task that a
Hmm.
human can do that AIs cannot do, right? And what we've seen in the last 5 years is again and again confident predictions about what AI will never be able to do have fallen, right? And so people, the skeptics have had to keep moving the goalposts over and over and over. Right.
Hmm.
I mean, 3 years ago, we saw, models that were just struggling with with basic arithmetic questions, or just with the most basic logical reasoning. Right now, a couple weeks ago, we saw several models that achieved gold medal performance in the International Math Olympiad, right? Which is something that 99.999% of humans would not be able to do, right? And
Right. Okay.
they would have said that it requires mathematical creativity, right? But already now we see people saying, no, this is not such a big deal because they only solved 5 of the 6 problems, and those were not the truly hard ones, right?
Uh-huh.
They didn't solve, the really hardest IMO problem that, of course, only a few of the humans managed to solve, right?
Hmm.
And so it's just like without batting an eye, people just, move the goalpost, right? And so now, we can say, okay, they are not yet at the level where they can write our research papers for us, right?
Hmm.
They can't, let alone can they, prove the Riemann hypothesis, or solve
Yeah,
the
yeah.
great unsolved problems of math or of physics or whatever. But I am not willing to confidently declare that is not going to happen, even just on the current path, right?
Okay.
Because I've seen, so many past confident predictions just be obliterated, right? I mean, people
Hmm.
said again and again, like it can't just be that purely scaling up a neural net and feeding it more and more data without understanding what's going on, right? That must hit the limit. That cannot work. That cannot give you,
Yeah.
passing the Turing test or anything like that. Okay, and the whole story of the last decade has been, the wrongness of that prediction, right?
Hmm.
Yeah, just pure scaling of neural nets, with more and more compute and more training data, has gone further than, the like all but, let's say, the very craziest, most wild-eyed people,
Hmm.
20 years ago would have ever dared to speculate that it would
Yeah, yeah,
go.
yeah.
So it's possible that, ultimately the skeptics will be right, that maybe, maybe things will hit a limit, right? I mean, I've only had a little bit of time, recently, to play around with GPT-5, which
Hmm.
just came out last week. But, you
Yeah.
could say maybe, the improvement of GPT-5 over GPT-4 seems like maybe less than that of GPT-4 over GPT-3, right? Seems maybe less dramatic. So maybe things are are asymptoting. Maybe there's some limit that will be reached, which is short of being able to automate all human creative work. But I'm not willing to say that with any confidence. I'm
Okay.
not willing to say that I know some deep principle according to which that's true. And like Deutsch apparently is.
Okay. That's fair enough. Okay.
Yeah.
One of the problems with AI is that, or LLMs, is that they don't get better over time like a human does. So like it might be
Hmm.
even the case that the AI baseline is at many tasks higher than a humans, but like there's no way you can give an AI a high level feedback the way you can with a human. And I actually saw this somewhere
Hmm.
that LLM seem to learn very roughly 100,000 times less efficiently than humans. So this is like
Hmm.
huge. And you're
Hmm.
kind of so stuck with the abilities you get out of the box. Um, and the reason like human employees seem to be very valuable and I guess also hard to substitute is that uh, they have this ability to learn from one's and another's mistakes and they really get better over time. So like
Hmm.
from your
Hmm.
perspective, is this like a fundamental like architecture imitation of current AI paradigm or could we
I
kind of
don't see. No, I
yeah,
don't see how it's fundamental. I mean, okay,
okay.
there's a couple things that are mashed together here, right? Well, I mean, one of them is, I mean, of course, these AIs are learning machines, right? They
Yeah.
do learn clearly, from all the data that they are trained on. Now, just because of the, commercial requirement that, you have to like build a model and then deploy it, right? And you can't just continuously, retrain it, for like a separate model for every user, right?
Right.
There is this, the way things work today, there is this training phase, and then there is a deployment phase, right?
Mm-hmm.
Where the weights of the model are fixed in place, and then that model is released into the world to interact with people. Okay. But even then there is what's called in context learning, right? So as
Mm-hmm.
do a chat session, let's say with ChatGPT, it is learning things about you over the course of that session, right?
Okay, yeah.
And actually its behavior is changing to be more like its best estimate of what you
Mm-hmm.
want from it over the course of that session. And I understand that AI companies are introducing more and more capabilities for saving things from one session to the next, right? So like the next time you log in,
Mm-hmm.
if you've set it, if you've chosen this, then it can remember things about you from that session. Okay.
Yeah, yeah.
Now, the next type of learning that we could talk about is that the companies themselves, right? They are deploying a model or they're testing a model and they're saying if this is not what we want, then we are going to train this model further, right? We are going to put it back in school, right? And of course,
Mm-hmm.
after the pre-training phase, right, there is this whole phase of reinforcement learning that happens where, you give the model carrots and sticks. You say, like, these are the kinds of outputs that we want to see more of. These are the
Mm-hmm.
kind that we want to see less of, right? And it does learn from that, right? Sometimes it learns too well, as we saw with the
Okay, yeah.
Mecha Hitler, right? Or with Google Gemini, I guess, going in the opposite direction and like making like multiracial Nazis, for example, because it thought it should just
Yeah,
make
yeah.
all the pictures multiracial, right? So, but now, the like a next step that many people have talked about, theorized about for decades, but maybe on the cusp of actually happening now is self-improvement. Okay, where an AI model would actually contribute to the research on how to train the successor to itself, right? How
Mm-hmm.
to build the next model. Okay, I mean you can say at some level that's already happening. Like if you look at the AI companies like Anthropic and OpenAI, right? Like the programmers there at those companies are making massive use of AI tools to write the
Mm-hmm.
code for the next models. right?
Yeah, yeah, yeah.
As programmers all over the world are making massive use of AI tools today, right? Already, AI is being fed in to sort of help produce the next generation of AI. Okay, but you could imagine beyond that, in AI that let's say a GPT-6 that is good enough that you can just ask it to design and train GPT-7, right?
Okay. Yeah, yeah,
And if
yeah.
you give it, enough, resources, you give it enough permission and control over the, data centers and computing
Uh-huh.
facilities that it could do that. And then the GPT-7 could design and deploy GPT-8 and so
Mm-hmm.
forth. Okay. This is what, a lot of people worry about would be, the beginning of the singularity, quote unquote,
Mm-hmm.
right? Where
Right,
AI
right, right.
just goes so far ahead of us that that it rather than us becomes the dominant intelligence on Earth, and we don't understand what would happen beyond that. Okay, um, so a lot of people would like us to not rush into the AI that can self improve in those ways, that
Mm-hmm.
can design something better to replace itself, at least until we understand much better how to steer these things in a direction that is that humans will be happy with.
Okay, okay, makes sense.
Hmm.
How is it possible that AI like has basically the entire compilation of human knowledge memorized, and it hasn't been able to like make any connection that has led to a discovery? Like if you have everything memorized, you would
Hmm.
probably be
Yeah,
able to say like, oh, this symptom leads to
yeah.
this kind of stuff. Like how is it possible that
I I mean, look, it's been 3 years, less than that, since ChatGPT came out,
yeah.
right? In that time, there has been massive improvement from, like, it's basically, these models have gone from like elementary school up through graduate school, right? In
Mm-hmm.
terms of, the kinds of questions they can answer, the kinds of reasoning that they can do, right? And my own experience as a student was that there was not some magic point when I became able to do research. It was just that
Oh, okay.
when I was a kid, I might rediscover math facts that were known hundreds of years before me, right?
Mm-hmm.
And then, when I was a teenager and I learned more, I might like rediscover algorithms that were known 50 years before me, right? And
Oh,
then I
okay.
got into quantum computing, and then I was very proud to prove this theorem, but then it turned out that this theorem about quantum computing that I had proved had already been published 1 year before, right? And then eventually a few years later, I proved something that was only discovered at the moment when I proved it, right? So
Mm-hmm.
so it was sort of like a continuous process, right? Of
Okay.
um, and look, I mean, DeepMind has used AI to make new, discoveries in math and science. But you could say that there are humans who are still sort of driving which questions to ask or what
Mm.
to do. And the AI is being essentially used, but it's being used in ways where it's not that surprising that AI could help, like finding better heuristics for finding new matrix multiplication algorithms or things like that. Okay, I expect that it is only a matter of a year or two until
Oh,
we
okay.
see some more impressive scientific discoveries than we've seen so far that make crucial use of AI.
Mm.
That would be my prediction. I could be wrong, but I just want to bet against a colleague named Ernie Davis, who thought that
Oh, okay.
there was no way that AI would win a gold medal in the International Math Olympiad until 2027. Okay,
Ah,
or before
okay.
through 2027. So we made that bet several years ago. I felt very confident in making that bet, which he's now conceded. Okay,
Yeah, yeah,
and so I also feel confident in saying yes, there, in the next few years we are going to see some interesting scientific discoveries being made by AI.
yeah. Okay,
Whether
awesome.
that includes proof of the Riemann hypothesis and things like that, that I
Mm,
don't know.
okay, okay.
Yeah.
So one core argument for AI safety that is that like systems can be extraordinarily competent at pursuing like a narrow objective, like
Mhm.
maximizing a stock market profit while being like unable
Mhm.
to evaluate or weigh the broader cost of achieving it, like destabilizing the financial system. So, do you think
Mhm.
that kind of goal smarts but value blind AI is a real risk anytime soon, or
Yeah,
like,
yes.
yeah,
Yeah,
go ahead.
yes, I absolutely do. I mean, we also see in humans, that it can be
Yeah.
dangerous when you have a lot of capability, with like either a stupid or an evil objective, and we certainly see that that is possible, that that happens,
Mm-hmm.
right? I mean, even leaving aside, the genocides and the horrible
Mm-hmm.
thing, some of which were pretty competently arranged and organized, with a lot of intelligence behind them,
Yeah.
right? But I mean, you see, rich people, spending their money in what the rest of us might say are just totally absurd ways, even though obviously it took a lot of skill and cunning, to get all that money, and they are pursuing whatever they think their goal is,
Yeah,
right?
yeah, yeah.
So of course it is a risk that people will, release agents onto the internet and say, just do whatever you can to, destabilize this country, right? Which is our enemy country, or do whatever you can to, accumulate Bitcoin for me. And, that will lead to a world with some very powerful agents, pursuing narrow goals that we may
Mm-hmm.
not like. Right? And this is even before you get to the world where these we would think of these intelligences as forming their own goals, right? That
Okay,
that
okay.
might be totally alien to ours. I mean, that's also possible. But even before that, of course, I would worry about these in many ways, superhuman intelligences, but pursuing whatever goals humans would want to give such intelligences.
Mm-hmm. Okay, okay. So,
Yeah.
okay, another problem in AI safety is that
Hmm.
I think we'll eventually face with AI or AGI, I might be confusing the names,
Hmm.
is that, and that not many people seem to address thing, but I'm sure that you've thought about it since you worked 2 years at OpenAI at AI safety, is that AI enabled coups. So like this could happen even in established democracies and could be staged by just a
Hmm.
single person, I guess. So like the way
Hmm.
this is possible is that military and government leaders could fully replace human employees with AI systems that are singularly obedient to them and eliminating like the need to gain human supporters for a coup and then secretly
Hmm.
loyal to them. For example, fully
Hmm.
autonomous military robots that
Yeah.
pass security tests but later execute a coup when deployed in military settings. And finally, like senior officials within AI projects or the government could gain exclusive access to superhuman capabilities in weapons um, or that kind of stuff, and increase their power until they can stage a coup. Um, how do you, how should we deal like with this effectively?
Yeah, all of those wonderful things might be in our future. Uh,
Right.
what can I say? So, so I have been a strong advocate for, we need to proceed with, respect for the enormity of what is being created, right? This is not, just another cool, little, technology that it's not just another consumer product, right?
Hmm.
This is a pivotal moment for life on Earth. Okay,
Right.
when we now have only the second example in the history of the planet of a verbal intelligence.
Yeah, yeah.
That and it's arisen, of course, not independently from our verbal intelligence. We're the ones who created it and who trained it, but it's arisen, in a completely different substrate, and it's
Mm.
very different from us. Uh, and so we ought to be proceeding, with caution. I was in favor of states like California, passing legislation to try
Hmm.
to, make sure that there's disclosure requirements, that there's whistleblower protections, that there's liability for harms that are caused. That unfortunately was vetoed. And now, given the current federal administration in the U.S.,
Hmm.
we would be lucky, to just not have, um, to have any safety,
Okay,
whatsoever,
okay, okay.
right? As opposed to just completely shredding everything in just a race to win
Hmm.
against China. And of course, you mentioned the dangers of democracy. I mean, we've seen how fragile democracy is even without AI,
Hmm.
right?
Yeah,
And
yeah.
so, of course, I'm worried about these things. I don't think that it's helpful to just like say, oh, this AI is just a stochastic parrot, or it's just, it's not, it's all just sort of a sham. I think the people who think that way are going to be blindsided by what's going to happen over the next decade. So I think that let's approach this with humility, with caution,
Mm.
and this is not just some cool consumer product release, right? This
Just a prediction. How far are we from AGI?
No, I don't make predictions of
Oh,
numbers of
really? Oh,
years.
okay.
If No, I don't. No, if I could do such things, I wouldn't be a professor. I would be an
Okay,
investor.
okay. Makes sense.
I mean,
Okay. Okay.
there were a few things that I could say with confidence, like gold medal in the IMO by 2027. That felt like a slam dunk to me. But
Okay.
AGI, I mean, for one thing, it will surely depend on how you define it, and
Okay.
people will even afterwards, if there are still people, then those people will
Mm.
argue about exactly what counts as AGI and what doesn't. So,
Okay, Scott. Thank you
yeah.
so much for coming. Thank you
All
for
right.
for your time.
Sure. No
See you.
problem. All right.
Bye bye.
All right. All right.
Yeah, enjoy
Okay.
your vacations.
All right. Thanks a lot.